welcome to the Explainer. Look, if you're tuning in, you already know the stakes. We are stepping right into the high-pressure arena of the MT2 certification practical exam. This isn't just about knowing magnetic particle inspection theory, right? It's about proving you can actually execute it flawlessly when the clock is ticking, the book is closed, and you are entirely on your own. Ultimately, your signature on an inspection report carries the absolute weight of safety and reliability. This exam is the gatekeeper, so let's get you ready to clear it. Here's the game plan for this explainer. 1. The practical exam breakdown. 2. Mastering amperage formulas. 3. High versus low fill techniques. 4. Crafting written instructions. And 5. Conquering actual test questions. All right, Section 1, the practical exam breakdown. So let's dive right in. Picture this. You're walking into the certification lab. You've got your specimens sitting right there in front of you. What are the absolute non-negotiable parameters of the test you're about to take? You've got no notes, no lifelines, literally just you and the equipment. Well, here's exactly what you're up against. You have a strict 8-hour time limit, and it is entirely closed book. That means 0 electronic devices are permitted in the lab. No cell phones, no tablets, nothing. You'll be required to inspect a total of 4 specimens. Specifically, you've got to execute 2 inspections using the wet fluorescent method and 2 using a yoke with black magnetic particle fluid. And pay attention here, because this is a critical pitfall. You absolutely must demagnetize the specimens at the completion of the examination. Failing to follow basic, mandatory rules like this, or say improperly using the yoke on the wrong specimen, can literally result in failing your exam on the spot. You have to score at least 70% on each individual specimen just to pass. Moving on to Section 2, Mastering Amperage Formulas. Okay, now for the part that honestly intimidates a lot of candidates, the math. Read this quote carefully. Formulas in MT2 aren't just arbitrary numbers to memorize. They're absolutely critical safety measures. Think about it. If you push way too much current through a part, you risk arc burns, which could completely destroy the very specimen you're supposed to be evaluating. These calculations are what we call rule of thumb formulas. The crucial thing to remember is that they only give you a starting point. Real inspectors use these empirical formulas as a baseline, just to get in the right ballpark, and then they verify the actual magnetic field strength using tools like a Hall effect Gauss meter, a pi gauge, or AS5371 shims. But to pass the exam, you absolutely must know how to calculate that starting line. What's really interesting here is how the math actually branches out depending on the specific technique you're using. For a straightforward headshot, the formula is 12 to 32 amps per millimeter of part diameter. So say you have a 10 millimeter part, you just multiply by 20 amps to get a solid 200 amp starting point. Easy, right? But the second you introduce a center conductor, the math totally changes based on whether it's centrally located or offset. We'll dig into that difference in just a second. Let's break down the coil method formula into a few visual chunks you can easily memorize. Step 1, identify your constant. For a low fill factor part, that constant is going to be 45,000. Step 2, calculate your length to diameter, or LD ratio. The formula is simply the constant divided by the LD ratio and then divided by the number of coil turns. But step 3 is where you really need to be vigilant. To guarantee sufficient field strength, your LD ratio has to be between 2:1 and 15:1. If your part exceeds that 15:1 ratio, there's no way around it. It must be inspected in sequential magnetizing shots. Section 3, High versus Low Fill. And that brings us to the specific nuances of using a central conductor. Your math depends entirely on how much of the hollow part that conductor actually fills. A high-fill conductor fills almost all of the internal circumference. It's super efficient because it simplifies the calculation. You literally just use the part's outside diameter, and it reduces the number of magnetizing shots you have to take. But a low-fill conductor sits offset inside the part. For low-fill, your diameter calculation becomes the central conductor diameter plus 2 times the wall thickness of the part. 4D. Seriously, commit this to memory right now. If you're using a low-fill central conductor, the effective inspection area is exactly 4 times the diameter of the conductor. 4D. That means a single shot only magnetizes a limited section of the cylinder. So to inspect the full circumference, the part has to be rotated, remagnetized, and re-inspected. And remember the golden rule here. To magnetize a part using the same field direction at a lower current value, you must first demagnetize the article prior to re-inspecting. Don't forget that. All right, Section 4, Crafting Written Instructions. Okay, so you've done the math, you ran the current, and you actually found the indications. Now what? You've got to write it all down. This quote really encapsulates the core philosophy behind documentation.
During the practical, you have to write an instruction for one of your 4 specimens. And the goal isn't just to prove to the proctor you found the flaw. It's to write a set of steps so perfectly clear that a completely different inspector could pick up your sheet, grab the exact same tools, use them in the exact same way, and find the exact same results. It is all about absolute consistency and repeatability in the field.
So, to secure that passing grade of 70% or higher on this portion, your written instruction has to be rigorously comprehensive. You must clearly list the scope of the inspection. You must document the personnel qualifications required. You need a highly detailed list of every single piece of equipment and accessory you used, the specific calibration procedures for that exact specimen, and, crucially, your exact equipment settings at the time of inspection, meaning the amperages you calculated and verified. And finally, Section 5, Conquering Test Questions. Let's see how all this builds into the actual testing environment. We're going to run through a rapid-fire review of test questions taken directly from the source material. Question 1. What is the name of the formula E equals I times R? This one really challenges your memory on the fundamental electrical principles that drive magnetic particle inspection in the first place. Boom! It's Ohm's law. 1 volt of electrical pressure will force 1 ampere of current flow through 1 ohm of electrical resistance. Understanding the relationship between volts, amps, and resistance is foundational to basically everything we've covered in this explainer. Question 2. Let's keep the momentum going here. What is the term used to describe the opposition to the flow of current in an electrical circuit? Take a second to lock in your answer. You guessed it, resistance. This dictates exactly how materials behave under electrical loads, which, of course, directly impacts the magnetic fields we're trying to induce. All right, let's do one final, highly specific, practical question regarding the wet bench method. A water break check is principally used to determine what? Proper wetting of the part using water wet stationary bench units. Look, passing this test requires mastering both the heavy math of the magnetic field and the fluid dynamics of the bench suspension. You absolutely need the carrier fluid to spread evenly so the particles can actually migrate to the leakage fields. Which brings us to our final thought today. When you finally sit in that lab, calculate your amperage perfectly, find the hidden indication, and proudly sign your name on that report, what does the weight of your signature really mean? Mastering these formulas and rules isn't just about passing a test for a piece of paper. It's about ensuring the structural integrity of the aerospace, automotive, and industrial components that you and I rely on every single day. It is literally about protecting human life through flawless, non-destructive testing. Good luck in the lab. You've got this.